So, I think we are ready for the second part of the lecture, which will now lead us to further up in the brain to cortical networks and how they might be involved in mammalian vocalization. And yeah, well, maybe in the first part I was a little bit too strict in saying, well, you know, animals can perform vocal behavior without cortex. They don't need cortex at all. Well, this is probably true for the vocal generation of the vocal patterns. However, these animals seem really to use their cortex or cortical networks to cognitively control their vocal behavior. And here I'm not speaking about the cognitive control or the learning of specific speech patterns, but how to use these vocalizations, so more vocal usage learning, so that these animals might be able to volitionally initiate their vocalization, so to control where exactly they want to utter a specific vocalization. And well, this is also a topic that is debated since quite a while actually, and we heard about this morning already, that there is this referential alarm call system in velvet monkeys. We all know things have changed, but just to, when we talk about the perspective, how it was in those days, so now 1980, so there were really some people that say, wow, that's really cool to see that there is an animal that is producing different call types in response to different visual stimuli, and so that maybe this indicates that these animals are able to really to control which vocalization to produce during which whatever visual input. So when they see a snake, they do a snake alarm call, or in response to leopard, a leopard alarm call. So that this was something that gave the idea, well, there might be some behavioral evidence that there is really something like volitional control on the onset of specific vocalizations. And there are also recent studies that showed such indications, and another example for that is a pretty recent study of Samahanto and Roy, who was a postdoc in Xiaoxing Wang's lab. So what they did is they played back noise bursts to marmoset monkeys to see how this is changing the vocal behavior in these animals. What you see here is a vocal trace. The whole trace is 50 seconds, each of these traces. And as you can see here, they did different experiments. In between here, you can see the vocalizations, these double phi calls, again, these monkeys are producing. And they're playing back so these 5-second white noise bursts. And it tends to be that these animals learn somehow that we have this periodic occurrence of these, actually it's 4-second white noise bursts, and what these animals did is that they produced their calls, or start to produce their calls in between these noise bursts. And they did that also when they were presented with aperiodic noise, which was still predictable for the animals, so there was some kind of repetition in that. It got a little bit harder for these animals, but they still tried to put their vocalization in between these noise bursts, probably to make sure to transmit again the vocal signal to the receiver. And this breaks down as soon as they used aperiodic signals, so unpredictable white noise bursts, that the animals weren't able anymore to position these vocalizations in between these noise bursts, so that they conclude about that, well, indeed these animals seem to have some control, not about the pattern of these vocalizations, but where to place these vocalizations, where to place them temporarily to avoid, for example, these masking noise effects. And something similar has been done by Roy and Agner together with Mark Hauser. They also used white noise bursts to interfere with vocalizations in monkeys, in this case with cotton-top tamarins. So these are using or producing these so-called combination long calls, which consist out of a introductory note and these 3 long harmonic calls they're producing. And what they did is they played back 500 milliseconds after the onset of these vocalizations, or maybe a little bit longer, 700 milliseconds after the onset, they played back a noise burst. And in these cases where they played back these noise bursts between the first and second syllables, the animals more likely didn't produce a third syllable. They only produced calls with only 2 syllables in normal situations, but when they played back these white noise bursts, they significantly more produced these 2-syllable combination long calls and not these whole version with the 3 syllables, so that they also concluded well. This also shows that the animals are somehow able to inhibit their output, so that they, when there is some interfering noise, that they are able to stop vocalizing, which also would indicate they have somehow control over their vocal output, right? And there are a few more studies that indicate from behavioral studies that there is something like this volitional control of the vocal initiation, and this led people since the 70s actually to try to train animals. So to say, okay, it seems that they're able to volitionally control their vocal output, the onset, so let's train them to produce these calls in a reinforced situation, reinforced conditions. And the people that were starting to do that were actually Sutton and when in Lindemann's lab, and also involved here was Chuck Larson, so that it actually really tremendous work. That was the first time that people really started to try to train monkeys to volitionally initiate the vocal output. However, you will see in this and several other experiments I will show, it's not that easy actually to train monkeys to produce a specific pattern volitionally when this behavior is actually innate and, more importantly, motivationally driven or emotionally driven. So really to separate whether this is really volitional or whether this is still emotional, right? But they were the first who tried that, and I think they did a pretty good job. So what they did, so their paradigm was to get the monkeys into the chair, into the chamber, which was actually also this time already something that people said, well, this won't work because rhesus monkeys do not vocalize when they are fixated in the monkey chair, maybe even when the head is fixated with the head post. However, they managed to get that animals to vocalize, and so they recorded the vocalization. So this is a 5-second trace of the vocalization with the acoustic signal and the average and rectified signal. And what they implemented here was a so-called go band. So what they did is, as soon as this vocalization went above a specific threshold, a specific amplitude, then a light went on in front of the monkey, and the monkey got a reward. So to say, okay, if you are above a specific amplitude with your vocalization, then you will get a reward. And they looked at, during the training sessions over weeks, how the behavior of these animals is changing. They changed in this way, so they did this with 3 monkeys. When they looked at the mean go time, so how often these vocalizations were above this go band threshold, so that the animals were experiencing the slide in front of them, they could see that there is a slight increase. So really that the monkeys really seem to produce louder vocalization over time, even though it took a while. So this down here are weeks, so 1 week to 15 weeks, so 3 to 4 months, to get these animals to increase their mean go time in this case. And when they looked at the correct vocalization, so how many vocalizations did they produce that went at least once into this go band, then they found quite a ambiguous result. One monkey who was already vocalizing a lot at the beginning, around about 150 vocalizations, went up to 500 vocalizations per session. Another monkey went up to 200, so also increased significantly the behavior. Another animal didn't really, it was quite ambiguous, so it first increased and decreased again, so probably didn't knew what to do exactly. And then they said, as a right, so each animal learned to produce the calls when a stimulus signaled the appropriate occasion, so that in that way that they really know when their signal is produced, they have to produce this vocalization. Now the question I try it again. So what do you think? Is this volitional initiation of a vocal signal? From our perspective, we would have today what we've heard so far. Or could it be still something else, driven by something else?
Just be stimulus response.
So you mean, for example, that just to that stimulus, because maybe that's also an important small. It's all about the little differences, but important thing to say is that each time when they produced the correct vocalization of the cause, they got a reward, and this reward were a few drops of apple juice, so that was kind of the money they were paid for. And then after that, they could directly produce another vocalization, then they got again apple juice, and then another vocalization, then so they could do one vocalization after the other to get their apple juice. Well, when we think, for example, as we said already, about this motivationally based or emotionally based point, that, well, it's still, I don't want to say that this is not a kind of a conditioned response what the animals are doing, but however, it's hard to exclude whether these animals are just responding to the reward maybe before. So the monkeys are producing a vocalization, they get a reward, and then they are in a specific mood, maybe in this food mood, so, oh yeah, there is something to drink or to eat, and then they're producing a food call, and a coo is, for example, a food call, and then another another reward is coming up, and then so maybe they're not really paying attention to this visual stimulus. It's just about, okay, I'm here in a situation, I'm feeling fine because I'm getting paid for whatever I'm doing. I don't really understand what I'm doing, but I get a reward for it. And I'm in this really cool coo situation maybe. Okay, maybe, as I said, it could also be there is already some conditioning in here, but it's really hard to disentangle what it really is, right? Okay, let's come to the next point. Maybe you can help me there. So there's another study that has been done recently by Gino Coudet in the lab of Leonardo Fogasi in Parma. So they now went also a step further, said, okay, there has to be some more limitations, so that the animals have to really get a cue, and so that they really know when we want them to do something. And so they initiated trials. So the trials were separated in food trials and no food trials. In the food trials, the animals got a little piece of food in front of them. So it was separated with a plexiglass shield so that they couldn't grab it. Then they had to produce a vocalization, and if they did so, they got a reward. So they could then, the plexiglass shield went down and they could take the food. And then they could eat it, and then there was, that was followed by a rest phase for 30 seconds, and this time the animals had to withhold vocalization and should not vocalize. If they vocalized there, nothing happened, they didn't get a reward, but then it started all over again with this food session. And when we look at the data, they trained 2 monkeys. They could indeed show that these animals are vocalizing. When they are vocalizing, they're especially vocalizing this food. In this food part of the trial, about 50 to 70%. However, they also did several vocalization in these no food trials between, let's say 16 to 25%. However, that was significant. So they did a Wilcoxon test and said there was a significant difference. They produced significantly more calls during the food period than during the non-food period. So what do you think? Could we say that this is volitional initiation of vocalization? Yeah?
I mean, this could simply be emotionally driven, I guess, because they see the food reward and they produce a food call.
Yeah, could be. So again, I know, so I talked to Leonardo and he told me that it took quite a while, a couple of months to get the animals to do that. So it seems that really something is going on in these animals. So it's really that they have to learn something here. However, it's, as you said, you could still think that it's still something going on, that there is some emotional trigger behind that, especially also since they're also producing cues in this rest phase. Yeah, so they didn't 100% get it to do their calls here and not here. Okay, so that was something what was out there. Actually, this study came out a little bit after I started also to think about that, and also to see, yeah, please?
But just thinking about this design and what you said with the rest phase, it would maybe have been interesting if they also had positive and negative reinforcement. You know, like for the birds, they do these no-go where the room gets dark, so we could have
Yeah. So they did no negative reinforcement. Yeah.
We might have seen really a strong reduction in the rest. Yeah.
Maybe. Yeah.
Because it's so hard to train them to vocalize in those food periods, it's already sort of punishment. So it's hard to produce this vocalization. This is really when they don't get a reward, they stop vocalizing it like almost immediately, right?
Probably, yeah. Okay, so as I said, this was all something that I was very interested in, whether we can really train these animals to vocalize volitionally. And well, I really had this unique opportunity to go into the lab of Andreas Nieder, because I think when you want to do controlled experiments in the lab, you have to go to Andreas Nieder, at least in Tübingen, or in Germany, I would say. There are many more, but he's one of the guys, I would say. I'm not in his lab anymore, so I can say that. So that we said, okay, we also want to train animals to volitionally initiate the vocal output. Don't worry, I will also ask you whether you think this is volitional initiation in our approach. So what we did is, so we also said we are training these animals to volitionally initiate the vocal output, but at first we said, okay, we have to define what is actually volitional initiation of vocal output. And so as we see it, the volitional call initiation is the ability to vocalize in response to an abstract learned sensory cue, and therefore the ability of the animal to instrumentalize its vocalization. So there has to go on some learning process before the animal is really receiving a reward, so that it's really something like a call and command what the animal is doing. And to put this in contrast to the spontaneous calls, that we say that the spontaneous calls are the adequate response of the animal to an unconditioned sensory stimulus, like for example, an alarm call in response to visual sight of a predator, or food call when seeing a piece of food, for example. So what we did is we trained also 2 rhesus monkeys, and we decided to do this in a straightforward go-no-go detection task. So the animals were sitting in a primate chair in front of a computer screen. They had a little bar in front of them. The animals had to grab this bar. Then a pre-cue appeared, which was your white square. This was shown for 1 to 5 seconds, pseudo-randomly chosen. And then, in most of the cases, in 80%, the animals were presented a go stimulus, which was a red or blue square. And in response to this square, the animals then had to produce a vocalization within these 3 seconds. So we trained 2 animals, kind of to figure out whether this is motivationally based. So maybe that the color red is something like a coup situation for the animals. We decided to train 2 monkeys with a different vocalization each. So we trained 1 monkey to produce coup vocalization. So this is this harmonic vocalization these animals are producing. There's this one here, these coups. And the other animal, monkey C, or also called Caruso, was trained to produce grunt vocalizations. These are very short, harsh, noisy vocalizations they're producing. With more these short calls. So when the monkeys did this correctly, they got a reward. In our case, they got several drops of water, and then they could proceed with the next trial. Now, to make sure that this is really that the monkeys are only vocalizing in response to this visual stimuli, we introduced catch trials here and there, which were also just that the white square proceeded for another 3 seconds, and the monkeys had to withhold vocalization during this time. And when they vocalized in this time, they got kind of an off for 3 seconds, or just the screen kind of got red, and which meant, okay, this was wrong. But not really a punishment, because, as I said, it's hard to train them anyway, and just to indicate, okay, this was not the correct thing you did. And so important also here to say, so this was completely computer controlled, because we also wanted to make sure that there's no interaction between the animal and the experimenter in any way, to exclude at least that. Also of course, this is something that we train to the animals step by step. So it's not like that we put the animals for 2 hours into a monkey chair and the animals had to earn their water. So of course we led them to this point in a very, very long procedure, so that the animal learned over time that these 2 or 3 hours when they are sitting in this chair, they are kind of getting their salary, so to say, in this case about water, and that they really learn, okay, per day I can work there for 2 to 3 hours, I can get all the water I need for the day, and when I'm done, I stop working. And that's actually what these monkeys are doing. So they're working for 2 hours, and after that they're stopping to work, which means they're putting their hands kind of the bar, closing their eyes, and that way, okay, I'm done, let's go, not to bed, but back to the animal facility. So they really decide when to initiate these trials and when to stop to do all these things. Okay, then due to the go-no-go paradigm we then defined. When they were vocalizing during the goal trial, it was a hit. They got a reward, current rejection when they didn't do a vocalization in the catch trial, and the miss when they did not produce a vocalization in the go trial, and the false alarm vocalization in the catch trial. So we trained these two animals for quite a while actually, and I want to show you one of the monkeys, so monkey T, also called Torkel, how he was performing the task. So this was the coo monkey that was producing these coo vocalizations. And what you see here is the monkey sitting in one of these typical monkey chairs you probably saw before. So down here is the bar that the monkey has to grab to initiate a trial. This is the tube where the liquid was, or the fluid was then presented, and this was the microphone just to record the vocalizations. And the screen you can see on the left side is the same screen that the monkey is looking at, so just that you can see what the monkey is seeing, right? And so when I'm starting the video, just pay attention here in this area where the monkey is grabbing, here in the middle part of the screen. So it's a very small stimulus, but you can see it, especially when it's changing the color. And then you will hear also some ticking, and this ticking is just that machine that is rewarding the animal, so that is the pump that is pumping the water into the tube. Okay. So the monkey is grabbing bar, color change, vocalization, drinking the water, every drop, okay. Starting again. Now the next trial is a catch trial. Starting. No. Well, okay, then he wanted to immediately start another trial, but here we have an off phase still for another 2 seconds just to make sure that the monkey is really not vocalizing after this trial. And then there's another vocalization. So, and this is something these monkeys, when they are well trained, and this really takes a while, a couple of months, then they're doing this over and over again as long as they want to get reward, right? And so this is now one of these typical a daily session that the monkey is doing. In this case, it was a session for about 2 hours that this monkey you saw before was doing. What you see here is the trials. So each line is one of these self-initiated trials the monkey initiated. They are all triggered by the onset of the go stimulus and catch stimulus, separated by go trials and catch trials, sorted by the length of this pre-cue. Now trials where the monkey produced the vocalization, they're indicated by a black dot, and this blue dot, this blue dot, and this blue dot indicates the onset of the vocalization within this trial. And these horizontal bars back here are indicating trials where the monkey did not produce a vocalization, so-called mistrials. And these mistrials, we'll see later, are very, very important for us, especially when it goes to neurophysiology. Okay, I think the picture is pretty clear. So the monkeys are almost exclusively vocalizing here during the go trials. This is here the median activity with a median latency of 1.5 seconds. To make sure whether this is significant or not. So what we used was the D prime value in this case, which is a standardized difference between the means of the hit and the false alarm rate. This case, and the successful performance is defined by a threshold of 1.8. So all sessions where we have a D prime higher than 1.8 indicates that this is a significant or successful session where the monkey was able to detect the signal, right? And so for this case, we had 245 go trials.
How did you choose this 1.8?
This is something, when you go through the literature, this is something that everybody agreed on, that this is some say 1.6, 1.8, so this is kind of, well, the values that we found, we said, okay, we take the higher value from these 1.8. More kind of a general thing here. And, well, actually in this case, you will see, that's a threshold, but we are far above this threshold, but this is a threshold we took. So 188 calls were done during go signals, which led to a hit rate of 76% roundabout. And in these catch trials, it did one false alarm, leading to a false alarm rate of 1.6. And when we are then calculating the D prime value, we come to a value of 2.9, which is really well above detection threshold. We did this for both monkeys for several trials. And what you can see here is now the pooled data of 15 sessions. So what we did is we did this curves here for 15 sessions and calculated the median response with the first and third quartile for both animals. And this is what you can see here. So it's kind of the median activity, the median latency, what the animals are showing in this behavior. They're both in that way pretty similar. That there are slight differences, but so the mean or the median call latency is around about 1.5, 1.6 seconds in both animals. And also important to say is that the D prime value is in both animals well above detection threshold in all the cases. So they're really able to do this. Yeah.
How do you decide when to stop the training? Is there individual training, like you said? Sometimes it takes a couple of months for a single monkey to be trained. When do you say training phase is over? Now we start testing.
The training phase is over as soon as we are at the stable. In this case, we defined that for this training, the training is over since when we have this a stable behavior that we can see really that really one session after the other was very well above this detection threshold.
Okay.
Yeah.
Mm-hmm.
Okay. Yeah. Okay, and now again the question, so is this volitional call initiation? Or could it be something else? Yeah?
Yeah, I mean, I would say this is more volitional call initiation because it's an arbitrary cue, light, and also you train the monkeys to do two different call types. So this would speak against a spontaneous call reaction.
Well,
isn't there anything that you could do better? What?
Each monkey has only one call.
Yeah.
So,
I mean, it could be still
so
motivation.
if you would
somehow.
have two calls, and but that is,
Yeah. So that. Yeah.
But still, there could be some emotional relation to the sign. So in the one case, the sign is just off, so that could mean like do nothing, or there's no emotional state. And the other one, there's a red sign that could mean, or you said you mixed blue and
red and blue, it doesn't matter, so it was all. Yeah.
But a color.
Yeah. So that kind of they react on this color and with a specific motivation. Yeah, William?
Yeah, the conditioning is not equivalent to volitional control, because in Pavlov's dog, you have an arbitrary cue in the end. The condition stimulus is the bell, and the dog is salivating. It can't help itself.
Yeah, well, but this is classic conditioning, right? It's not operant conditioning.
Yeah.
So the animal cannot. It's just the animal is doing something that just to stimulate it somehow. He's doing the one thing and just gets the bell, and then it's kind of okay. It's just hearing the bell and then doing the vocalization. In this case, it's more like that the animal has to learn in the behavioral task that it has to produce a specific vocalization in response to an arbitrary cue that had nothing to do with that at all, to then get afterwards a reward. But still,
What's the context of the calls are given usually?
Yeah, so the coup calls, so both calls are communication calls on the one hand, so long distance and short. Like the coup more long distance, grunt more short distance. But I have to admit they're also food calls. So especially the coup is also a food call. So what I've heard, believe it's so the point. It could be still could be somehow emotional, right? Since you could so well. It takes 1.5 seconds. Maybe the animal has kind of to get into a specific emotional state to produce a specific vocalization. Well, from data in humans, we know there are some data in humans from human actors where they measured also latency, how long it takes for the actors to evoke a specific emotion in these animals. I don't recall how exactly they measured that, but they measured that in these actors, and they got latencies at when the actors did really hard, they got actually short latencies like 1.5 or 2 seconds, but that was really something very, very short. So this would really mean that these monkeys are better than humans in this case. Well, it could be, we don't know. However, we heard this a lot actually, that well, this could be, there's still maybe a slight thing that this is maybe motivational. So what we then tried, actually, as you said, actually, okay, maybe more convincing would be to train these animals to produce two vocalizations, right? In response to different cues. So we did that. So we did a discrimination task. So we trained these, and now we split these visual cues and added to a symbol. So why that symbol? That's not important. It's just for neurophysiological reasons. For data analysis later on. So it's just important. There are two different cues now for coos and for grunts. And we trained, I have to say, we tried to train both animals to perform with this task, to produce coos only here, grunts only here, and to produce nothing here. Of course, the probability kind of decreased to produce a correct vocalization in a specific window. And well, this was really something what we found out. This is really kind of the edge or the limit what we can get these animals to. Since from now on I just have to talk about monkey T, so about Torkel, because we were able to train the animal to perform this task. The other animal wasn't able to do it. So it really seems that this behavior was somehow kind of the limit you can get these animals to kind of control the vocal output. However, in this animal, I think it was still pretty convincing. So these are again these trials separated, these grunt and coo trials and catch trials. The blue dots are trials where they produce coo vocalizations, the green dots where they produce grunt vocalizations, and so they produced actually most of the grunts during the grunt trials, most of the coo during the coo calls. But what you can also see is that here these horizontal lines back here, they increased dramatically. So the animals did a lot more mistrials since they sometimes, it seems that they were just confused and didn't know what type of call they should do, which can be also seen here when you look first at the deep prime. So the deep prime for the coos and for the grunts, that well, there were some trials where they were really good, well above the threshold, but in most of the trials there was some kind of moving around these thresholds. It was kind of, yeah, it's they are still able to do it on this way. However, so when you also do here a Wilcoxon, we also get a significant difference. Though that they do much more coos during the coo, much correct, more hits in coos than false alarm, and also during grunts. Another interesting thing what we find out, well, this is probably only anecdotal since it's just one animal, but what we saw in this in Torkel, that the latencies actually were different for these two vocalizations. So what you see here is the call response latency related to the cue delay, because in this we also want to know whether the cue delay was changing in correlation to the call latency was somehow related with the cue delay, the preceding cue delay. This wasn't the case, however. They were much faster to produce this grunt vocalization, this monkey, than producing the coo vocalization, which is especially interesting since this monkey was trained to do coo vocalizations first. So this is something that he should be really good at. And then, as an add-on, he had to produce grunt vocalization. Therefore, he was much faster. Maybe grunts are more easier to produce, or maybe there are different mechanisms underlying between grunts. So maybe we have actually indeed two vocal pattern generators. We do not know from this part, but if you have any idea, I would be happy to discuss that with you this evening or the next days, of course. Okay, so as I said, we found this in one animal, so that which was in that case a pity, because of course we then wanted to proceed with neurophysiological methods to really get into the tissue to see what part of the brain is controlling this behavior. So we decided to step back and say, okay, both monkeys are doing the same, they're both doing this detection task, and each of these animals is producing one vocalization, so that we have two animals. One animal, neurophysiological data of one animal is always very hard to convince reviewers to get it published. So we're thinking about regions which we could tackle in the brain, which could be kind of capable to control this behavior. And well, even that we've heard yesterday about that maybe Broca's area is not the ideal region to look at when it goes to human speech, we still say, well, we wanted to tackle this region because first of all, as we also heard yesterday, there is aphasia at least the first weeks after a stroke in this area. So it has to do something with vocal speech, and also there was I cannot recall the author now, I have to look that up, but so there was a study coming out 2 years ago where they showed that this Broca's area is especially involved in the initiation of vocal signals. So not so that it's more kind of silent during the vocal signals, so when human speech is produced, but that the initiation of these vocal signals seems to be controlled by this Broca's area. So this would still be ideal, since we're here about vocal initiation, right? And another cool thing is that there is, since we know from Pandia and Petrides, there is a monkey homologue of this Broca's area in macaque monkeys. So we also have here area 44, which is here within the arcuate sulcus, and area 45, which is prior to the arcuate sulcus. This area has pretty similar psychoarchitectonics as the human Broca's area, and also the cortical projections are very similar. And from one study, also from Petrides, we know that in anesthetized macaque monkeys, when we are stimulating within the arcuate sulcus, they could elicit jaw movements, lip and tongue movements in these anesthetized animals. So it really seems that this area is also somehow involved in the control of the articulatory muscles. So we decided to record in this area. So we put our 2 monkeys into a scanner and made an MRI to see, okay, where exactly is the arcuate sulcus within these 2 animals. Arcuate sulcus is here, and we then implanted a recording chamber. We recorded mainly in the monkey homologue of human Broca's area, so area 44, which is here within the arcuate sulcus, area 45, both animals, and also we had a couple of recordings in area 6, so the premotor cortex. So, and what we were able, so we were recording around about 1,000 cells, 1,000 units. So this method, of course, a little bit different to MRI. So when we do fMRIs to measure activity, with fMRI you can measure the activity of several hundreds or millions of neurons in the brain. With this method we are measuring one neuron after the other. It takes more time, but we have a more precise idea about the timing of the activity of these neurons, and of the also of the position of these neurons. So it's something like that we have it's something like statistics, right? That you have a huge population of neurons, and you're just taking out, let's say in this case, 1,000 neurons, and then you can conclude from this randomly chosen neurons what the population of these neurons is actually doing. And actually about 150 neurons from these 1,000 neurons showed vocalization correlated activity within this region, and this is one of these candidates. So this is now the activity of a single neuron in response to these trials, to these vocal trials. In blue, so the blue trials are the trials where the monkeys produce the vocalization. They correlate by the onset of the go stimulus. And the red trials are the trial where the monkeys did not produce a vocalization, so these missed trials. And this was extremely now important for us, because of course the animals are doing a lot of things when they're sitting in a monkey chair, and we are in a highly cognitive area, so which is also responding to visual stimulus, to you name it, and you will find neurons in the prefrontal cortex that are encoding this behavior. But we know that in the missed trials the animals are perceiving the same stimuli than during the vocal trials, and the only difference between these 2 situations is that the monkey is producing a vocalization during the vocal trials, right? So that we then conclude that the changes in activity between hits and miss trials is actually vocalization correlated activity. And this is something you can see here. So the blue vocal trials, we have this increase in neural activity. This is well prior to call onset, so the call onsets were in this range here. The first call onsets were about here. So we have a neural activity that's well prior to vocal onset. And this was also true when we looked at the population of these neurons that actually showed such a pre-vocal increase in neural activity, shown here as a so-called population response of these 58 neurons that showed such a
Actually, I just don't understand how it's locked to the go onset or it's locked to the call onset.
In this case, to the go onset.
Okay, but because it looks like, how can it be locked to both?
Yeah, this is a little bit confusing. So the thing is that the onset of the vocalization, of course, are not all on one line.
That is the average
This is
time.
just the average time. So and there are these yellow dots you barely can see. So this is just, so they're locked on the go onset, and this is just the median onset of the vocalizations, right? Down here it's a little bit more clearer. So this gray shade area is the distribution of the onsets of the vocalizations. And this is the population response. Again, this is that's the mean activity of all these neurons with the standard error that are showing this behavior. So these were neurons showing increased activity. We also found neurons that were the other way around. So neurons that showed this vocalization correlate decrease in neural activity. So that prior to vocal onset, the neural activity was decreased in some way. And this was also true then when we looked at the population that we were from neurons that showed such a behavior, that there's a clear decrease in neural activity. Now we had a closer look on these excited neurons. So neurons show this increased neural activity, and we looked whether we find differences in the activity when we separate the neurons to the regions where we recorded these neurons. Instead, we were recording in area 45, 44, and area 6. There were also a couple of neurons. And this is the population response of these neurons. In this case now, it's triggered to the onset of the vocalization. So this is all the pre-vocal activity. And what we can also see here is that so this pre-vocal activity is predominantly shown in area 44 and 45. There's barely anything going on in area 6. Also, I look at the y-axis, so there's this around 0.5, and here a really clear response prior to this vocalization. So that really indicates that area 44 and 45 are preliminary encoding this behavior. So the volitional behavior. Yeah. Okay, so what we can say with that is that we have neurons in the monkey homolog of human Broca's area that are encoding vocal behavior. However, the question is, are these neurons firing prior to conditioned vocalizations, or are they firing prior to whatever vocalization the animal is producing, right? Also maybe spontaneous vocalizations the monkeys are producing here and there, or is this really something correlate with this cognitive behavior? And here we were extremely happy that one of these animals, again tortoise is kind of the star in the lab, produced calls in between trials here and then, so that we were, this animal, able to compare the activity during spontaneous calls and these volitional calls. Again, this is now an example neuron that we were recording, again triggered by the call onset. The call offsets are distributed somewhere around here. I think this is a nice picture what we see in this neuron. There is a clear pre-vocal activity prior to these volitional calls, and there's almost nothing going on during spontaneous calls. Of course, we're all to do this in a fraction of neurons to compare that. Of course, this number was much lower since, due to that we needed a sufficient number of spontaneous calls, and they were actually produced very rarely. And this is now in this small fraction of neurons where we had a sufficient number of spontaneous calls. Again, the pool data, and what we see is that there is a really nice pre-vocal activity prior to this volitional calls, and there is almost nothing going on, or a little bit, but almost nothing going on during spontaneous calls. So that with these data, we think that we can show that this monkey homolog of human Broca's R is actually encoding predominantly these volitional calls, these cognitively controlled vocalizations, and not the spontaneous calls. So this is really that this region that is so important for human speech is already involved somehow in the initiation of vocal behavior in primates. Yeah?
It's really nice story. But what I'm wondering is why is it so, what do we learn from the fact it's so hard to get these monkeys to do this? You have to work so hard in training them. But then, it seems like the neurons are there ready to. So why is it so difficult to hook the system up in this way? That given that the cells are there ready to.
That's a very good question. So one of the ideas is that so since it's really this is maybe also an argument that these calls are really more effective than volitional, that it's really hard for these animals to hijack the system in a cognitive way, and that they have to be trained, at least these rhesus monkeys have to really be trained for a long time that they are able to perform this behavior, right? However, yeah?
I really like this, so I just want to make sure I understand it 100%. When the electrodes are in BA 44 and 45, in spontaneous production of calls, nothing happens. There's no activity in those.
Not as much, but there are some cells who had also increased activity, but this was still significantly lower than during the volitional calls.
Yeah, okay. Yeah. By volitional calls, because we use the term a little bit differently, you mean that the monkey had to initiate the trial themselves, they had to respond to the stimulus, they had to know if it was a red one and if they were supposed to talk and not a white one and all. So, I mean, there's an analog in the human fMRI literature for tasks like this where you have to, it's not just about naming an item, for example, it's about deciding between items and when you're supposed to initiate the vocalization and when you have to hold back. So in other words, there's more going on. There's more, it enters the realm of cognitive control, which a lot of people have written about regarding the inferior frontal gyrus. The issue is sort of where along the inferior frontal gyrus. It's used in Sharon Thompson-Schill's stuff, the posterior inferior frontal. Might be related to this, might speak to this effect that you're seeing here. It's less about vocalization and more about, am I supposed to start the vocalization or not? Or, I have to keep track of if it's a red call, I grunt, or coo, and if it's a white one, I don't. Do you understand what I mean? And
so you mean
it's also a cognitive control issue. It's not just initiating a call. So I find the distinction really interesting between these two conditions.
So was it a question or a comment?
Yes, sorry. A bit of both, yes. So I wanted to make sure I understood that in the spontaneous calls, you're not seeing the extent of the activity in these electrodes in 44 and 45 as you do with this task that they have to do.
Yeah.
Okay, that's really nice.
Thank you. Yeah. Nevertheless, there are criticisms, especially since, well, we are training these animals. We're training these animals for a long time, so that we hear here and then, well, we are training animals to do an artificial behavior, and this is just artifacts, what the training artifacts you're measuring, right? Because it's artificial behavior. Well, first of all, for me it's hard to say what is really artificial behavior, because the animal is able to do this behavior. So it's somehow embedded in his repertoire. So it is, for me, this is a natural behavior from the animal. But nevertheless, I was very happy that actually last year a study came out where they also recorded in this region, in the, let's say, the ventrolateral prefrontal cortex in another monkey species, but nevertheless in marmoset monkeys. And we have a pretty same picture in that pretty same picture, and I will tell you a few seconds what this in my view means. So this is a study, a very recent study of Corey Miller, and so he used this antiphonal calling paradigm again, having one monkey in one cage and the other in the other monkey, then recording from this animal while it was vocalizing. They're doing these phi calls. He was recording also, well, it's hard to say whether Broca's aria or whether there is something like a monkey homolog of Broca's aria in marmosets. However, area 45 is also down here, so you record out in the ventrolateral prefrontal cortex. And while the animals are performing vocal communication, they actually see that there's also an increase in neural activity and a decrease in neural activity. Well, the latencies are a little bit shorter than we find, but nevertheless they found neural activity in this region, which also might be an indicator that these animals actually also using this volitional control of the vocal output in their everyday life, right? Since we can find also these freely moving animals when they're vocalizing with their group mates, we can also find neurons here, these all these black neurons, these vocal motor neurons in the ventrolateral prefrontal cortex of monkeys. Okay, so this is the PFC, ventrolateral prefrontal cortex, that probably is hijacking the system somewhere. And the question, of course, the next logical question is, on which level is this PFC hijacking the vocal motor network? And well, the first idea we had is, since there are connections between the ventrolateral prefrontal cortex and the anterior cingulate cortex, it might be the ACC, since this area is also involved in the vocal behavior, in this innate vocal behavior. And so we also recorded in the anterior cingulate cortex while the monkeys were performing this task. But here I don't want to say too much, since there is a very nice poster this evening of Natalia who did that work. But just as a teaser, also there are neurons that are showing similar, still different, but also similar response to these conditioned vocalizations. Okay, that's the last point, almost last point. I want to briefly talk about also audio-vocal interaction on these levels, so on cortical levels. So whether also there we find audio-vocal integration processes going on, since, well, vocal production on a cognitive level, that's the one thing what we need for complex communication. But on the other hand, we also need, well, auditory feedback, so that really vocal communication can happen on a complex level. And actually, I think we are seeing this figure now for the third or fourth time in this meeting. However, as we know in humans, there are these nice connections between the auditory cortex and the Broca's area, and they are also present in the rhesus macaque. So the question is whether we also can find this in the rhesus macaque, maybe cells that are integrating this behavior. And actually, when we just look on the auditory side, there are some studies that have been actually done already in this region. For example, the very nice work of Liz Romansky that she started in the lab of Goldman Rakesh. So she was recording actually in this area in awake monkeys, in this ventrolateral prefrontal cortex, a little bit more anterior than I did, in the dimple. However, still ventrolateral prefrontal cortex. And she found a discrete area of where she could record cells that were active only during the presentation of species-specific vocalizations, but not during other vocalizations or other acoustic stimuli. So these are three example neurons that show activity during different monkey vocalizations. And there is also a study from Gilda Costa, don't know whether I pronounced it correct. That's a PET study where they looked whether they found regions that predominantly respond to also to species-specific vocalizations in relation to non-biological sounds. And they find a region also here in the ventrolateral prefrontal cortex that's probably here area 44 somehow, as it seems, which also shows a higher activity during these species-specific vocalizations in comparison to non-biological sounds. So also there seems to go something auditory on in this region. So since we had these monkeys, these vocalizing monkeys, we want to see how these neurons are showing on the auditory side, are active on the auditory side. So what we did, we have our go trials and catch trials. So what we did is we kind of added something to the catch trial, so the monkey wasn't vocalizing but was still in a controlled situation. And there we kind of extended this no-go stimulus for another second and then played back an auditory stimulus, and we chose a grunt vocalization for the grunt monkey and coo vocalizations for the coo monkey, so that we then also can compare these two stimulus, so the stimulus and the production of the vocalization when recording these neurons. And what we found, first of all, which is always nice, we could replicate the data, that mostly that we could also find auditory neurons in these regions in area 44 and 45. So this is the activity of 3 example neurons. This is the length of this coo vocalization. So these neurons are from the coo monkey. Different types of auditory responses, phasic, phasic, tonic, some complex responses. So there are auditory neurons in this region. And of course we were now interested how these neurons are responded when the monkey was vocalizing by itself. And well, what we can find was pretty surprising for us that about half of these neurons actually showed audio-vocal response properties. And here's an example of these audio-vocal neurons. And these type of neurons, what they're doing is they're showing, when played back an auditory stimulus, or this cue stimulus, they show an auditory response, in this case a phasic response. And when the monkey is producing a vocalization, they are responding down here. So this is the activity of the same neuron like up here during self-produced vocalization. And what we see is that there's also somehow a phasic, maybe a little bit broader, increase in neural activity, but this activity is prior to vocal onset. So it seems to be more a motor or initiation process going on here, and there is even a significant decrease in neural activity during the call. So it really seems that this is kind of filtered out, this vocalization, or this information. And so that this indicates that there are also somehow these audio-vocal integration mechanisms that are really crucial for evolving some complex audio-vocal communication system like human speech, for example, is at the end, that there is something like that also in rhesus monkeys, and maybe also in the last common ancestors we had with them. Okay, so that as a second summary, I hope that I could convince you that we have evidence for volitional control of vocal output in rhesus monkeys, and that we were able to record neurons in the monkey homologue of the human broadcast area that were encoding this volition call initiation, and that also some of these neurons were showing audio-vocal response properties. Now, at the very end, there is one slide still left. I want to also here kind of focus on that this is not the whole picture. So we can show, okay, these animals can volitionally initiate their trials and they can volitionally control at least the initiation of these calls. However, it seems that there is something more going on, that it's even more complex, and this is since we actually found out over the last years that something is changing the behavior for these animals. So we train these animals now since a couple of years, I think 3 or 4 years, where we do all these experiments. These animals actually are still alive and they're still working in lab. However, they are not part of this vocal conditioning process, experiment. And the reason for that is very simple. They stop vocalizing. So this is now the response or the behavior of these two animals that we had, so monkey C and monkey T. These are the correct calls that produce per session over time. So we start with both animals at round about 5, at the age of 5, and they stop both at round about the age of 8 years. So and we have a slight decrease over this time during all these sessions where we measured the activity of these monkeys. And this was not only the total number of these vocalizations, also when we look at the hit rate, also the hit rate decreased significantly in both monkeys. Actually this monkey completely stopped. This was the very last sessions he also stopped, but in the last kind of block where we recorded that he was still kind of trying, and that they were kind of trying something. I think what you can see here pretty nicely is these animals were still initiating trials, so they were still motivated to perform the task. However, they were not vocalizing anymore, and this got severe, and this decline from session or from block to block that we were working with these animals. And this was not due to the fact that maybe the animals forgot to perform this task, since the false alarm rates were still very low, and there was no some correlated increase in false alarm rate over time. So they were still able to perform the task, but they weren't able to perform these vocalizations anymore. Now the question, of course, is why? Why are they? Oh, by the way, I forgot that. So a lot of things changed in these animals. Also, the call latency changed. Actually, in both monkeys significantly. And actually, one of these monkeys, it went up from 1.5 seconds to 2.5 seconds. So they were almost not able to get this 3-second window anymore, because it took them so long to vocalize. Then the question is, why are they doing that? Of course, we were discussing that pretty extensively, and of course one idea could be they're just just cognitively, just have a cognitive decline, right? The animals, they're just not able to learn tasks or to perform tasks anymore. And therefore, actually, we trained these animals in a new task. What we decided to do a delayed match to sample task, so where the monkeys were shown a visual stimulus, and then there was a little break, and then we showed the second stimulus, and when this was the same stimulus, the monkeys had to indicate that there is the same stimulus by releasing the bar or just not releasing the bar when there is a different stimulus. So more or less kind of a similar experiment, but with a manual response and not with a vocal response. And these are the results actually here, the blue bars back here. So in very short time, in a couple of weeks, actually these animals were able to perform this task pretty nicely, and also with high correct responses. They were back at 80% again, and even more sessions. So it's a manual response that's easier for the animals. They did up to 600 sessions per day. Vocalization was about between 100, 150, 200, depends on which phase we were at this moment. So there is something going on. Now, of course, that would be really interesting if you have some ideas there, what could have changed in these animals. So I think the best idea we could come up with is that, well, when we correlate this to the age of the animals and about the transition between different phases in their lifespan. For example, here the juvenile period, which lasts in these macaque monkeys to around about the age of 6 years, and then they have the transition into adulthood. That one idea might be that these animals are losing somehow the ability or the flexibility to perform this volitional calling after they enter their adulthood. But again, this is just a guess. We don't know this yet. We might should do some more experiments on that with the next monkeys. So there are the next macaque monkeys that are under training and also are on a nice stage already, right? Yeah?
Do you see this kind of decrease in the wild as well? Is there much of a decrease in the non-in-lab animals that are in the wild? Actually, there are some studies that show that juvenile monkeys are producing more vocalization than adult monkeys. Spontaneous, but this is hard to say whether this is spontaneous or not. But there is also, and they're also producing different kinds of vocalizations. Does it make sense? They have a greater variety of different call types they're producing within time range.
How old do monkeys get?
These monkeys, well, in lab they can get up to 10, 12 years.
How old are in the wild? This is monkeys 18, 20.
Yeah.
So this is middle age?
Yeah. And we have some Obergurgl cats that are 28 or 30.
Yeah, so there's something about their living in the lab, in fact, too, because it shortens their lifespan, and it seems to speed up this process of...
Well, it shortens the lifespan, since at the age of 12 they normally go into a final experiment. So these animals are they're still in good shape when they're 12, but normally at the age of 12, so the animals are getting, how should I say this in a nice way? So it's much easier to work with juvenile monkeys or with monkeys at younger age, so that when they're getting 10 or 12, when they did a specific task over and over again, it's really hard to train these old animals to a new task, because they stick with their task. That's something they learned their whole life, and they don't want to do anything new. So it's really hard to learn them anything new, and these new monkeys are much more.
Is there also a restriction of how many surgeries they're allowed to have? At least
That might be well possible. At the time I was working with these animals, it was not a restriction, but I wouldn't be surprised if there is a new restriction.
They get bored with the task.
Hey, please?
They get bored.
They get bored with the task. Yeah, that.
No, there's more to it. We just did a study on aging in the wild and in the monkey enclosure, where they get up to 28 years old. And there is something about that middle age period where they stop exploring, for instance. They are not interested in new things anymore. And I suspect that there is already some, maybe correlating, lesser degree of flexibility in all sorts of domains, not just in this kind of domain.
But is this unique to the lab animals?
No, because the monkey super testing is in France in a monkey enclosure that has 20 hectares and they're living in paradise, you know.
And I think another point is also that, well, they might get bored, but actually this is the time where they are earning their fluid for the day, so they are highly motivated to work there. And they still there, since they are highly motivated due to the, to the motivation to get the fluid, they are not able to do it.
So in humans, the speech that we produce is much longer utterances than these calls, I guess. And that also requires that there's vocal control of breathing. Mm-hmm. Is there any indication that there's volitional control of breathing? There's volitional control of breathing possible in these monkeys? And the second question is, if I remember correctly, but there was this paper a long time ago by Jürgens showing that in humans there's this separate pathway, separate tract for the volitional control that is not seen in other species. And that's an additional thing that happens.
Yeah. So that's
and that still is a finding that holds, or that still is a finding that still is a kind of finding that's solid.
Yeah. So that's another thing. So that this, even though that if the prefrontal cortex is able to hijack the system, so to evolve something as speech, of course, several other things have to happen. So the other thing, what one could think of is that this is, if you want to speak about precursors, I know we have to be careful about that, but this is kind of, if you say that speech evolved with evolution, right? Then there has to be some first step towards from these innate calls to, if we are going with this I know there are also several hypotheses how human speech evolved, but if you say maybe this evolved out of these innate vocalizations, you could say, well, then the first step has to be to get evolutionary control over the system, and then maybe there's the next step to be able to modulate these calls, maybe in a broader range that it is able in these innate calls, and so on and so forth.
But because this is, I think, if I still may continue here for 1 second. So of course there are theories that say that, in fact, human language has its precursor in gestures, right? Not in. Now this, and of course that always has made me a bit wondering why evolution has come up with this expensive machinery of an additional pathway and voluntary control of when we could do with gestures as well. So therefore I was never convinced that the gestural precursor was a kind of a story that makes much sense. But lots of people still believe that that's the right story. So you agree that that's not a very likely story?
That it evolved out of gestures? That I don't believe that?
Yeah.
No, I don't believe that.
Thank you. Yeah.
Stan?
I have a question and a comment. The question is, prefrontal cortex in these animals presumably projects to the striatum and ultimately gives rise to projection. Does it affect the vocalization? Has it been explored?
The striatum?
The projections, the involvement of the striatal pathway in regulating these vocalizations. Has there been any exploration of that?
Not yet.
I think that would be
valuable.
The comment is in listening to the totality of this, it seems to me the single thing missing to make this a vocal learning system is an auditory memory. It's created early in development and then projects to these structures and affects the response properties of them. And if you put that in these animals, you would have animals that all the substrate is there. You will see it tomorrow. All the substrate is there. That is quite similar to what is seen in zombies.
Yeah,
There's one thing that hasn't been described. So if you wanted to look for an aha moment for the evolution of vocal learning, these guys, it's the auditory. the memory, the formation of an early memory, and
Okay.
it's quite interesting.
Well, to be honest, just to be sure and to make sure that we are in a region where we have the highest probability to get such neurons. Of course, maybe this is something we will proceed continue to do, also to look on the right side. But there are some lateralizations already in the monkey brain, actually, also in the ape brain. There are something like also in this when it goes to auditory fields and stuff like that. But of course, it's not like that like in humans that it's exclusively on the left side, not the right side. Most of the case, you have a larger area on the left side than on the right side. But yeah, so actually the only reason why we record on the left side is we said, well, the human broadcast area is on the left side, so let's stick with the left side. Yeah.
Yeah, sorry. I would just like to know if you have any thoughts on that neuron that you found that had both activity when it produces and when it hears the call, that it was curious that it did not produce any like firing rates for after it hears himself, because the monkey can hear himself. And it's curious at least, right?
I would say, well, this is actually something you can find everywhere in the brain where it comes to audition. So there are actually in the auditory cortex, there are nice studies from Xiaoxing Wang. They recorded in the auditory cortex, and also there you can find auditory neurons, and they are inhibited during self-produced vocalization. You can find these neurons in the colliculus inferior, you can find these neurons in the brainstem. So this seems to be, they seem to be there really to filter out these self-produced vocalizations, and they're more masking the auditory input when they're vocalizing. Some neurons, of course, they are checking whether the vocalization is properly done. However, in most of the cases, it's the vocalization you're producing by yourself. As soon as you know, okay, the vocalization is uttered as it should be uttered, there is no sense about integrating or analyzing self-produced vocalization anymore. Yeah? Okay, then. So at the very end, I'm still at the beginning somehow of my career. Of course, all of this stuff wouldn't have been possible with a lot of collaborators and colleagues, and especially I want to thank Andreas Nieder, where we did all these monkey stuff. Natalia Gavrilov, who did a lot of the training and of the data analysis, and Walter Metzner, and yeah, of course, Uwe Jürgens, where everything started, and yeah, the Deutsche Forschungsgemeinschaft, which is actually kind of paying my whole lab at the moment for the next 3 years or 4 years. So yeah, and thank you for your attention.